Lecture 7.1, History of Cosmology, Part 1. Cosmology is the study of the origin, structure, and evolution of the universe. It addresses big questions such as how did the universe begin? Did it have a beginning? Is it infinite or finite? Static or dynamic? What is it made of? What will be its ultimate fate? Will it last forever? And so on. This lecture will be an overview of a timeline of cosmology starting in the 1800s and going up to the mid-1900s. In the next lectures, we'll go into some more of the mathematical models underlying these ideas. So in 1826, Olber posed an interesting question. He observed that if the universe is static, infinite, and filled with stars uniformly, the night sky should be as bright as the surface of the sun. To understand his reasoning, we imagine looking at stars farther and farther out into the universe and asking how much brightness those stars contribute to the overall glow of the night sky. So the picture on the left shows looking at different distances out. You'll see more and more stars, but of course each star will be fainter. The one on the right is an animation showing how the sky should look according to Olber's as you include stars that are successively farther and farther away from us. So our sun is the closest star, so we would see it. As we expand our radius outward, we should see more and more stars. So we see a few stars, and then they keep filling in more and more and more as you look out into the universe. So ultimately, as you include stars out to infinity, every patch of sky that you look at should have the same surface brightness as our sun. So this argument will proceed in two parts. In the first part, we'll establish that the surface brightness of a star does not depend on its distance. That is, the surface brightness of the sun will equal the surface brightness of a sun-like star halfway across the universe. The second argument will look at the amount of angle or the solid angle that stars take up in the night sky as we move out into the universe. So let's take the first part. Imagine that you are looking towards a star. The radiant flux from the star is given by the inverse square law. So as the distance to the star increases, the flux goes down as the distance squared. The solid angle, that is the two-dimensional angle of the star as seen from the Earth, also obeys an inverse square law. So as you increase the distance to a star, its solid angle goes down as r squared, as 1 over r squared. This means that the surface brightness is independent of distance. So the surface brightness, or the specific intensity of the star, is just given by its flux per unit solid angle. So if we take the flux of the star and divide it by its solid angle, we plug these two expressions in, and we see that the radiuses cancel. So what you get is just a constant number. So for the sun, if we plug in values for the sun, given its luminosity and its radius, we get that the surface brightness, or the specific intensity, is 2 times 10 to the negative 7th watts per meter squared per steradian. So again, that doesn't depend on how far away the sun is. It's just a constant. Okay, second part of the argument has to do with how stars are distributed through space. So we'll call n star the number density of stars in the universe. That's the number of stars, say, per cubic meter. R will be a radius of a spherical shell centered on the Earth. dr will be the thickness of the shell. And dn star is going to be the number of stars in that volume of space defined by that shell. So the surface area of the shell is 4 pi r squared. The thickness is dr. So 4 pi r squared dr is the volume of the shell. You take the volume times the number density will give you the number of stars. So the fraction of the sky covered by stars in the shell is given by that number density of stars in space times the solid angle of those stars divided by 4 pi, which is the total number of steradians in the sphere. So when you plug in this expression for dn star, the 4 pi's cancel, and you get this expression. So the important thing to observe here is that the fraction of sky covered by stars in a given shell doesn't depend on the distance. It's just some constant value that depends on the average radius of a star, the number density of stars, and then the thickness of the shell. But this quantity does not depend on the distance. So stars that are halfway across the universe will cover the exact same angle in the sky compared to all the stars that are very close to our solar system. So the total fraction of the sky covered by stars with the distance less than r is, well, we just integrate this expression. Again, it doesn't depend on r, so this just turns out to be a constant. When you integrate it, then you pick up the factor of r. So the fraction of the area of the sky covered by stars just linearly increases with that with that maximum distance that we integrate out to. Another way of saying that is that the entire sky will be covered when that fraction f is equal to 1. So if we plug in 1 here and then solve for that radius, you can call that the Olber's radius, and that's the distance that you have to go out into the universe until the entire sky is just covered in stars. So no matter where you look in the sky, you'll be looking at the surface of some star. So what this means is that if the size of the universe is larger than the Olber radius, then the sky should be completely covered in stars. And since, again, the surface brightness of the star doesn't depend on how far away it is, it means that the night sky should be glowing with the surface brightness of a typical star. So every little patch of the night sky should be glowing just as brightly as the surface of the sun. But it's not. So thus the paradox. So the question is, well, why isn't the sky glowing as bright as the surface of the sun? So this night sky is dark. What gives? What's going on? And it turns out that the first person to come up with a reasonable solution to this was Edgar Allan Poe, the poet. So he said, in 1848, he said that the night sky is dark because the universe had a beginning, which is kind of remarkably profound and kind of poetic. So it's very fitting that this solution came from a poet. So here's how this works. If, say, the universe is 14 billion years old, we wouldn't be able to see stars farther than 14 billion light years away because light from those distant stars wouldn't have had time to get to us. So I have 16 here and like 14 over there, but that's supposed to be a 14 there. So the idea is, like, if you imagine all of space as being filled with stars out to infinity, but that if there was, say, a Big Bang, if the universe had a beginning 14 billion years ago, then the idea is that that the stars farther out here would be there, but if they just turned on 14 billion years ago, the light from these stars would be traveling towards us and wouldn't quite have had time to get to us in the 14 billion years that the universe has been around. So if we were kind of looking out, it would just appear dark out here because those stars wouldn't have turned on yet. So the light from those stars wouldn't contribute to the surface brightness of the night sky, and that's why Edgar Allan Poe says that the night sky is dark. So it's kind of nice that there's a very simple observation that the night sky is dark. We can already infer something about the universe as a whole, that it had a beginning. Of course, there are some subtleties to the argument, and there's other ways of getting around this paradox. But basically, I think this is actually still accepted to this day about the reasoning behind why the night sky is dark. Okay, so that was in the 1800s. We're going to fast forward to 1912. We already talked about Henrietta Leavitt. She was the discoverer of Cepheid variables that can be used to measure distances to galaxies. So here's an example of a Cepheid variable. It's kind of bright, gets dimmer, dim, and then kind of brightens up and brightens up. So if you plot the intensity or the luminosity of the Cepheid variable as a function of time, it has this very regular appearance. And from the period of the Cepheid variable, you can infer the luminosity. From the luminosity and its apparent brightness, you can get the distance. So this was a major accomplishment in being able to measure distances out into the universe. A couple of years later, after Henrietta Leavitt's work, Albert Einstein proposed his theory of general relativity. We're not going to have time to go into general relativity, but John Wheeler has a famous quote that summarizes it. It says that according to general relativity, matter tells space how to bend, space tells matter how to move. So if you have a massive object like a galaxy or a star, its mass curves space-time around it, and that curvature of space is what we feel as the force of gravity. Once space is curved, if you have another object moving through that curved space, it will follow the curves of space, kind of like rolling a ball around a curved surface. So in a nutshell, that's the basic idea that gravity has something to do with the curvature of space. Okay, so we're going to use this curvature parameter k later on. So you can have a positive curvature, which means that if you're on the surface of a sphere, that's an example of positive curvature where the k parameter is positive. Negative curvature would be like on the surface of a saddle, and zero curvature or flat spacetime would have a curvature parameter of 0. So we know that space is curved around individual objects like stars and galaxies, but what about the universe on the largest scales? Does space as a whole have curvature in the universe? That's a cosmological question. And that is something that we'll be looking at in the next few lectures. When Einstein was formulating his theory of general relativity, he realized that the solutions to his field equations showed that space should be unstable, leading either to a collapse of space or an expansion of space, but it wouldn't be static. And so to get around that, because he thought that the universe was infinite and static, he introduced this thing called the cosmological constant to kind of counteract the force of gravity trying to destabilize space. Turns out that had he had more faith in his own equations, he could have discovered the Big Bang, because in fact the universe is unstable. But in trying to keep a static universe, he introduced this kind of fudge factor, this cosmological constant. So he later called that his greatest blunder of his career. In 1917 and 1922, De Sitter and Friedman solved the Einstein field equations and showed a variety of different dynamics to the universe. And then in 1927, Lemaitre, who was a Catholic priest, showed that the field equation specifically predicts an expanding universe, that the universe should be expanding, and he went farther to propose the Big Bang theory as the origin of the universe. That the Big Bang was some kind of explosive event that created the universe, which sent it flying outwards from something he called the primeval atom. So it's interesting that Lemaitre, a Catholic priest, came up with this notion of an act of creation, that the universe was created from this primeval explosion, and that it's been expanding out ever since. So it's interesting to note that everything we've been talking about so far has been all theoretical based on Einstein's theory of general relativity. There's been so far no mention of any experimental or observational evidence for an expanding universe. That came later. So in 1929 was when Hubble measured the recession velocity of galaxies and their distances. He measured the distances using Henrietta Leavitt's Cepheid variables. He measured their velocities using Doppler shift. So here's an example of 4 different galaxies. Here's a nearby galaxy in the Virgo cluster. You can see these 2 little absorption lines have been shifted from this line here to slightly longer wavelengths, indicating that it's moving away from us. As you go to more and more distant galaxies, the spectra of those galaxies is shifted to longer and longer wavelengths. So this galaxy down here is more distant. It's also moving faster away from us. So we can define the redshift z of a galaxy as the change between the observed and the rest wavelength divided by the rest wavelength. So you can think of it as kind of a percent change in where the spectral lines appear. So according to relativity, the observed wavelength is related to the rest wavelength in terms of the radial velocity v sub r. So c is the speed of light, and so relativity predicts this relationship. If you take the limit that the radial velocity is much less than the speed of light and do a Taylor series expansion on this square root, you can get this nice simple relationship between the redshift of the galaxy and the radial velocity. So the redshift is just the radial velocity divided by the speed of light in the low velocity limit. So that's how Hubble measured the radial velocities and the distances to the galaxies. So this is a plot from his original paper. On the vertical axis is recession velocity in kilometers per second. On the horizontal axis is distance in megaparsecs. So Hubble found that the more distant the galaxy is, the faster it's moving away from us. So the Hubble Law is this very simple relationship that says the recession velocity is this constant, the Hubble constant, times the distance to the galaxy. So distance is measured in megaparsecs, velocity in kilometers per second, and so the Hubble constant is in these kind of strange units of kilometer per second per megaparsec. This value is something that cosmologists are Very interested in measuring. It's changed over the years. It's very difficult to get a good value. Right now, the accepted value is around 70 kilometers per second per megaparsec. Here's a more recent version of the Hubble Law, going out to much farther distances than was in the previous diagram, and you can see a very good relationship, nice trend between those between the distance and the velocity. And finally, here's a picture showing Einstein and Hubble standing on the bridge going over to the 100-inch telescope at Mount Wilson. Our class walked along the bridge when we went over there. So anyway, that's it for this first timeline. In the next lecture, we'll be talking about the expanding universe in more detail.